Hi, now we'll talk about pre-processing and pipeline in the SQLs. So here in this lecture, we'll discuss how do we pre-process the data, right? And how to create a pre-processing pipeline using SQLs, right? But before that, here we are importing all the stuffs. By now, all of you are now familiar with these imports, right? Here we are importing the dummy classifier, this dummy classifier, and the dummy regressor. Now these imports, like here we have imported simple imputer for the pre-processing, and then for the splitting the data we have imported few stuff, and then we have also done some pre-processing modules. Here we have imported the SVC, which is a machine learning algorithm, and the decision tree classifier. From the utils we have imported everything for the plotting and everything, right? So here these are the imports that we are doing. So what we'll learn from this lecture, we'll see the basics of this, like the motivation for pre-processing, like why do we need to pre-process the data in the machine learning. We'll identify which transformation we need to kind of transform, such as like imputation, scaling, one-hot encoding, all these things in the machine learning development pipeline. We'll also learn this SQL transformers for applying feature transformations, right? We'll also discuss this golden rule in context of feature transformations, and then we'll talk about the pipelines, right? So as in motivation, so far we have seen the three machine learning algorithms like decision tree, KNN, and SVM with the RBF kernels. We have discussed the ML fundamental. That is, in the ML fundamentals, we have discussed like what is the significance of trained uh, data set, what is the significance of validation, and what is the significance of test data set. We have also discussed about how do we do the cross validations, what are the fundamental trade-off, and what is the golden rules. Now, the question is, are we ready to do machine learning on the real world data sets? So now, whenever we'll start working on the real world data set, very often we'll kind of consider that we need to do the pre-processing before, like pre-processing our data before we build a machine learning models, right? As an examples, in the homework we have learned about the k nearest neighbor on the Spotify dataset, where we were predicting a particular song, right? But the question is like, can we use the KNN classifier for this task? The intuition is to predict whether this user liked the particular song or not. Let's say that we have the query point, right, or a particular song. Now let's say that we want to classify whether this particular user will classify or will like that song or not. So first, for the KNN, first we need to find the song that are closest to the query point, right? And then we'll kind of use the vote on the target. So basically, let's say that we'll find the first five, or so here we'll use this top five closest data point. Then we'll vote the classes, and then we'll take the majority vote on the target, right? So this is how the KNN works. Now, in order to run the code here, you can if you want to run this code, right, you can download the dataset from the Kaggle, right? Here is the dataset. Now, this is the dataset, like Spotify dataset that we are doing. We are splitting the data. We are separating the training and like X and the Y part of that for both training and the test data. Here we have initialized the dummy classifier, and then by using cross validation, we can check the score. Here the score we have is in 50%. Now let's try the KNN classifier. When we try the KNN classifier, we can see that our score is 54%, right? Now, KNN is also not performing very well in the cross validation. That means it should perform well because this is a working very much similar to the random classifier, that is dummy classifier, right? And whenever, again, this is the model we have, right? So let's take the two song sample from the data set. Here we have taken the two song. Now when we check the equilibrium distance of the two songs, here, how do we see? So here we can see that this is the equilibrium distance we have, right? So the distance we have is very high. And here we have taken the equilibrium distance of these two songs by using all the features. Now let's select only two features. So here we are selecting now duration ms, this feature and the tempo. Here we have the tempo, this feature, right? Now we have selected the subset of the feature and then we try to check the Euclidean distance. So what do we see over here? Here the Euclidean distance using all the feature and using two feature does not change. So the distance value does not change. So what is problem over here? So the problem we can see is these two feature will dominate. These two feature will dominate this entire examples. Okay. Now here, what we see is our distance value is completely dominated by the feature with the larger value, right? Here we can see that all the value except duration ms and the tempo, all the values are having a comparatively very lower values, right? And that's the reason, right? So this distance value has been dominated, right, by these two feature only, right? Now the feature with the smaller value is being ignored. So the question is, does it matter? Of course, it matters. So the scale is totally based on how the data was collected, right? So let's say that duration m is, so let's say that uh like this is a kind of a millisecond. We can think of this as, right? Even though if we not, right, but consider that our duration was measured in the millisecond, right? And but the other value is not very much small value we are using, right? So that's the reason, right, the scale is matters, right? And the feature on the smaller scale can be highly informative and there is no good reason to ignore it. So we want our model to be robust and not sensitive to the scale. So the question is, was this a problem for the decision tree? So actually in this decision tree algorithm totally work very differently, right? There, so like even though we have used this pre-processing, but but this algorithm totally works in a different way, right? They consider each feature individually, right? And that's the reason we didn't had any problems, right? So how do we do that? So we can do the scaling using standard scalars, right? Which is a type of a transformer, right? Here we are importing our standard scalars. We are creating the object of that. We are applying fit method. We are transforming the train data. Now using the same scalar, we are transforming the test data as well. Here we can see the original data looks like this is our original data, right? And when we check, like here we can examine the few value of the training data, right? Here we're checking that like the first row of the energy is 0.61, and like after that what we're doing is when we like here we have taken the actual value, then the mean of the energy and the standard and divide by the standard deviation of the energy, and then the value we are getting is this. So the standard scalar, this transformer, is what it essentially does. Basically it essentially transform the data based on the standard scaling technique, and the standard scaling technique is we take the value, subtract that specific value with their mean and divide by the standard deviations. So here we are essentially doing the same thing. We are taking the value, subtracting with the mean and divided by the standard deviation, and then we have got these results. And this is the transformed data or the scaled data we have, right? And and yeah, and here we can check that this is our energy value, so which is same as like minus 0.318. This is also same as minus 0.318. So we are getting the same value over here, right? So now we know how the standard scalar work. Now how does fit and transform work? So sklearn uses fit and transform for the feature transformations, right? We fit the transformer on the training split and then transform the train split and the test split as well, right? So we apply the same transformation on the test data as well. That means whatever the transformation that has been learned by the training data, learned on the training data, the same transformation will be applied on the test data, and that is how we should do. That is how a best approach is, right? As an skill and estimator, so what do we do is, if you have the model like the classification model or the regression model, we fit the model on the training data, and then we predict on the train and the test data. We can predict on the train and the test data. If you have the transformer, this is if you have the estimator, that is the classifier or the machine learning model. If you have the transformer, so what do? We fit the transformer on the train data, and we transform the train data and the test data. Here we do not use the predict method, we use the transform method, and that is what the significance of transformer is, right? Now, do we so the question is, do you expect this dummy classifier result to change after scaling? Basically it will not, right? Because dummy classifier does not consider even the feature data, right? It will only consider the y value, right? Here we are trying to we are trying to check the scale neighbor classifier without scale and after scale. So this is the result that we are getting. So the train score is 72% and the test score is 52% without data scale, and after data scale, what do we see? So the training score is 79% and the test score is 68%. So there is a jump we can see in the test score after we scaled the data. So this completely gives the result or give the signal that after scale we can see the significant improvement in our result, right? Now, now the common pre-processing technique do we have as an, so basically we have the imputations. So this imputation help you to deal with the missing value, the scaling which will help you to deal with the numeric feature, and one hot encoding which will help you to tackle the categorical variables, right? So if you have the different type of problems, right, for that there are different type of there are different type of transformation that we apply on the data, right? Now again, in the next part of the lecture, we'll build ML pipeline for the California housing regression data set, right? And we'll talk about the different feature transformations, right, on that. But before that, let's talk about imputation and scaling. How do we do that, right? Like here, first we are splitting the data, and then we are trying to check the baseline. Here we'll be working with the California housing data set, right? So let's read the data. We are splitting our data into the training and the test part. This is the data we have, right? And here our y value is median house value, right? Now some column values are the mean and the medians, but some are not, right? So what we're trying to do is, here we have created another features, right? Here we have created a room per household using total room and the household for both training and the test data. Same as here we are creating a bedroom per household and the population per household for both training and the testing data we have created. So here essentially, as we know, some column has the value as a mean and the medians, but some are not. So what we're doing is, we have created a feature called feature called like room per household, bedroom per household, and the population per household. So essentially we have created three features over here, right? Now now let's see, the here we are just trying to check the first five example of the data. Here we can see that we have created the three features. Now, the question is, should we remove the total bedroom, total room, and the total and the populations? So probably because we have created these room per household, bedroom per household, and the population per household features, which are more relevant for this task. We can drop or we can leave. This is up to us, right? So here we have drop. Here we are dropping our columns, right? Now we can do the EDA part. So after the data splitting, right, you can do the EDA part right here. We have just taken up the first five examples. We can check the info, which will give you the, so this info is the function which is from the pandas. right? Which will give you the name of the column, how many number of non-count element we have, what is the data type of the column, how many number of columns we have, right? Here with the described feature method, we can see the all these numeric statistics value for the numerical data, right? And here we can, like, you can also get some missing value, right? And this missing value you can see by looking at the counter. Like here we can see bedroom per household has a lower value compared to the other features. So that's the reason. Let's say that maybe this bedroom has had some missing value, right? We can count how many number of missing value we have. We have 207 value. So this is all these techniques comes under the EDA, right? Here we are trying to check the histogram for each feature. So these are the histogram for each features we have, right? And here we are applying here we are doing the plot of basically here we are applying the actual plot using longitude and the latitude. And here we can see, and again, this color code is like a median household value we can see. So more blue means a lower value, and more red means a higher value. Here we can see that all the household is on this kind of band, right? Like on this area has the higher income, and these household has the lower income, right? Now, now these all we can kind of get from the EDA, right? Now, what all transformation we need to apply on the data set, right? So here, what we see from the EDA is we have some missing value. Scales are very much different across column. We can see that. So we can see the scale value are totally different for each features, right? Now, categorical variables we have, like the Ozian proximity are the categorical variables we have, right? So what do we do over here? So for now, we are dropping our categorical value. So we are dropping this Ozen proximity, and of course this y value we are dropping. And so basically we are separating x and the y part of the data from both training and the testing. And because currently we'll not do any pre-processing on the categorical data, so we are dropping our categorical data as well, right? Now let's first run our dummy regressors, right? Now here we have created a function called mean standard crosswell score. This function will help you to kind of take the mean and the standard deviation on the validation data by applying cross validation score functions, right? So here we'll do the same thing. So basically here we are using this cross validate function, right? Now this dummy regressor model we have, now we are passing this dummy object to the mean standard crosswell score, and the result we are getting as 0, because this is our dummy data we have, right? So our test score is kind of 0.505, and the train score is also very much same. Now let's do the imputation. So here we have this X data looks like this. We can see that. Here we have some NaN value we can see with the bedroom per household. So now when we apply the KNN, like let's say, like if you try the KNN model with the NaN value, with the missing value, right? You will get problems. Again, here we have hidden it, right? So we are not running it. But if you run this, you will get error. You will get error with this value error, and it will says that input X contain the NaN value. And that's the problem you will have, because the KNN consider all value and pass this NaN value to kind of distance function to calculate the distance value, right? So our classifier is not able to deal with the missing value or the NaN value we have. So the question is, what are the possible way to deal with the problem? The possible way is we can delete the rows, we can replace them with some reasonable value, right? So deleting the row, maybe it's not choice, but we can replace the value with this with some reasonable value, and for that we can use the simple imputers. So the simple imputer is available in the sklearn, which will help you to deal with these problems. We can impute the missing value in the categorical columns with most frequent value, right? And you can impute the missing value in the numerical columns with the mean and the median. So if we have the categorical column, we can impute with the most frequent value. If you have the numerical value, So we can impute with the mean and the median of the columns, right? Here, when we do the sort of the bedroom per household, we can see that all the nan value we have. We can check the shape. The shape is this, so we have this approximately 2000 data. Here we have initialize the simple imputer object. We are applying the fit method on the training data, and then we are transforming both training and the test data. That is how do we use with the transformer, right? So again, after you do this, and like if you check, do we have any nan value or not? You will see that there will be not nan value you will find, right? Now let's talk about scaling. Now in the scaling, right? So basically, this problem affect the large amount of ML method, right? That means if your data is not scaled, right, your algorithm will not work properly, right? You can read some articles over these on these links, right? But mostly we use a standard scaling only, but we have the other scaling method as well, like over here. And how the scaling affect the data, we can see from here. We can see that we have the original data. So here we can see that on the x-axis our range of the data is between 10 and 15, but after the standard scaling we can see that now our data is scattered around, and it is all scattered around between -2 and the 2, right? And again here, this both data, like this red and the blue data, is kind of centered around the 5 value, but now if you apply the standard scaling, it will be centered around 0. So now we have a good distribution of the data. Min max scalar, if you use, you will get this kind of transformation. Robust scalar will mostly transform your data. It's a standard scalar only, but it's like we just trip out some of the data from their like from the tails, right? So basically it's like we only consider the specific part of the data, right? Like we remove the data from the like from the first quarter, and like from the last quarter of the data, right? So that is, but again, mostly people use the standard scalar and the robust scalar, right? So again, the question comes, when do we use which one? So if you have the outlier in the data, a lot of outlier, you would want to use the robust scalar, and otherwise you are good to go with the standard scaling technique, right? So if you want to import any scaling technique, we just need to import from the pre-processing module. Here we are importing this min-max scalar and standard scalar. We have initialized this standard scalar. We have, now we can do the fit and transform together with fit underscore transform method. And then after that we can apply the transform method on the test data, and here we have the transformed data we have, right? So earlier we had imputed data, right? And so earlier we had the imputed data, and then we are transforming our data, right? Now after that, when we try the k-neighbor regressor, we can see that on the score, or like on the training data, we have achieved the 79%. Big difference we can see in the KNN training performance after the scaling, right? Now let's talk about feature transformation and the golden rules. So the question is, how should we carry out the cross validations, right? Last time we did discussed about the cross validation, which is a better way to kind of assess the model, right? How about trying the cross validation with the transformed data? Like over here, we are using the cross neighbor, this k neighbor regression. First, we are transforming our data using standard scalar, and then we are here we have this, right? So this is this is like transforming our imputed data, and then we are passing imputed data to the cross validations. Here we can see that the result we can see for the test score and for the train score. So what is the problem if we, like here we have the problem. So what the problem we have? Like if we pass the pre-processed data to the cross validation, what is the problem we have, right? So so the question is, when we pass the entire transformed data to the cross validation, and we already know that the cross validation testify our model on the test data, which was a kind of like which is a part of this training data only, right? So here we are not testing our data to the actual value, right? Here we are testing our data just like the training data only. So essentially what we can do is basically this is a kind of a data leakage problem, right? That means if we transform our training data, right, and then we test our it's like if we transform our training data but we do not transform, like if we fit and transform our training data and then we again transform our test data, that is what the proper transformation is, right? But essentially what we're doing over here is we are passing the entire transformed data, right, to the training and as a test data as well. So this is this will cause a data leakage, right? So here the question is, are we applying fit and transform on the train portion and the transform on the validation portion in each fold? No, it is not happening that way. So it's like we are applying fit and transform for each training and the validation fold as well, right? And that is what the data leakage is, right? So basically we need to apply the same pre-processing steps to both train and the validation data, and with many different transformations and the cross validations, right? You have to write a lot of code, right? And essentially there can be a mistake or like data leakage problems, right? Now to tackle these things we can use the pipeline method. So what the pipeline does, basically pipeline will combine all the transformation, right, and it will combine all the tasks in just one modules, right? So how do we use pipeline? We can use pipeline using scikit-learns, right? So here we need to import the pipeline from the pipeline. Like here we are importing pipeline from the pipeline modules, right? Here we are using the pipeline, right? And now in the pipeline we need to pass kind of each transformation, right? So like over like consider that we have the data and then first we want to do the simple imputer, then we want to do the standard scalar, then we want to do the k-neighbor regression, right? So all this can be combined in this pipeline. Now again, here for every object, here we know that these are the class, right? So we need to create the object. For every object, we need to have the object. Like for every class, right? Like if we'll initialize all this class, right? So we'll have to store somewhere to these objects, right? So here we are here we have to give the name for each transformations, right? With the string. And this is a bit of headache, right? But alternative, what you can do is you can use the make pipeline method. So which is a shorthand for the pipeline constructor, right? So instead of pipeline, now we can use the make pipeline. Now in the make pipeline again, you will do the same thing. It will also be kind of imported from the pipeline module only. But in the make pipeline, you do not have to pass any unique name for each transformation. Like over here, we were giving the unique name for each transformation, but here we do not need to provide any unique name. After that, now this pipeline will handle first, it will handle the simple imputer, then it will handle the standard scalar, then it will handle the k-neighbor regression. All the tasks will be handled automatically. Now we just need to pass pipe.fit to the training data and every step will be applied over here, right? Now, when we call the fit on the pipeline, so what will happen? So over here, first it will do the fit on the simple imputer on the training data, then transform xtrain using fit method, and it will create a new object. Again, this new object will be passed to the standard scalar and it will create another object, right? And this object will be passed to the k-neighbor regression. So essentially, every step is being handled one by one, right? And we can essentially do pipe.predict as well, and this will do the predictions, right? So what is happening over here when we apply pipe.fit, right? Again, I have said, or like again, I have already explained, right? Again, the same thing, whatever I have explained, that is explained in this graph, right? So when we apply pipe.fit, first it will do mm, fit on the first transformation, then again transform on the first transformation and create a new object. Again, this object is uh, passed to the second transformation with the fit and the transform, and then create a new object. Again, this object is passed to the classifier, right? And then it will give you the new object. When we apply the predict method, so in the predict method, it will simply does the transformations on the data. It will not apply the fit method. So if there is any transformation it's to be happen, that transformation will happen, right? And it will not apply the like here we can see that we like in the predict method, this fit method is not being applied, right? So when we do the cross validation, so basically cross validation will do the task, right? So if there is any kind of if there is like if we'll pass pipeline to the cross validation, what will happen is if there is any validation data, so for the validation data it will do only transformations, and for the training data it will do fit and transform both, right? So that is what happens. And here we are trying our result with the cross validation, and we can check that what test score is 69 and our train score is 79, right? So the pipeline will help you to solve that cross validation issue, right? Now the question comes, how do we handle the categorical features, right? Earlier we had dropped our categorical feature, which was Ocean proximity, right? But we can use it, right? Over here we had this training data, right? All the features, like all the data we had, right? And here now we are not dropping, here we are not dropping this where was it, right? So earlier we had dropped the this ocean proximity, right? And yeah, so here we have just selected the, like here we have just separated x and the y part of the data, right? But when we do pipe.fit, but because in the pipeline we have this k-number regression, when we do pipe.fit, right, this will fail because of the non-numeric data. Because now this time, because now this time we'll have the ocean proximity columns, right? And because of the ocean proximity columns, right, now this algorithm will not work because we have not encoded that data, right? So how do we deal with that? So, so the so the question is, can we use this feature in the model? Of course, you can use, right? So in scikit-learn, most algorithms only understand the numeric input, right? And so, what are the options for that? We can drop the columns, which is not recommended, or we can transform the categorical features to the numerical one, right? Now, to transform the categorical features to the numerical one, we have the few like we can do the two things. We can do the ordinal encoding and one-hot encoding, right? So one-hot encoding is mostly used, right? Ordinal encoding is used if there is any ordinal data. Otherwise, most of the time we use the one-hot encoding only, right? So here, let's check. Let's first create a toy data set. These are toy data set we have. Here we have all these categories. So we have this column called language. We have this category like English, Vietnam, Mandarin, and like French, Spanish. All these column we have, right? So let's try the ordinal, which is not. So these languages are not ordinal, but again, if you have to apply ordinal, how do we do that? First, we need to import the ordinal encoder, right? So here we are importing the ordinal encoder. We are applying fit and the transform. Now, after the after the ordinal encoder, it will return you some transformed value. And when you check, like here, we have concatenated our transform data and our original data together. And what we see is this English has been considered as 0, Vietnamese has been considered as 5, E has been considered as 0, Mandarin has been considered as 3, right? So basically, what has happened is it has it has given numbers, all the numbers based on the alphabets in the English, right? Based on the alphabetical orders, right? But here we can say, so this is how the ordinal transformation works, right? But in general, this is not the ordinal data, but in general, label encoding is useful if there is any ordinal data. That means if you label if you encode the label, basically if you say that which priority as at what point, like like the star rating has the priority, like the star 1, star 2, star 3. These are the priority, right? So now you understand that review with the star 5 is the highly rated, review with the star 1 is the lower rated, right? So we have to give this priority to the model, right? We'll talk about that later on whenever we'll use this one hot encoding, right? Whenever we'll use this ordinal encoding. Now how about one hot encoding? So here, this one hot encoding create a new binary columns to represent our categories, right? So if we have the C category in the column, it will create a C new binary columns to represent those categories, right? Again, consider our same language data we have. We had this data. Now, what will happen if we transformed these data to the one hot encoding? Now to transform the one hot encoding, we have to use this one hot encoder, right? Let's import this one hot encoder over here. Now here we are getting here we are initializing this one hot encoder. We are applying fit and transform. Then after the transformation, what we see is here we are seeing the output of all the, output of this transformations. Now what we see is here we can see that. So for each category, we have created a one different column. That means on the first, what was the category? The first was English. So for the English column, it will be 1 and all the value will be 0. What was the second column? For the second column, we had the second row, we had this Vietnamese. And when we see this Vietnam in the second row, we can see the Vietnam has 1 and all the values are 0. So this is how one hot encoding work, right? So it creates a binary columns for each category, right? How do we do it on the housing data set? Basically, we can apply fit method on the column data set, right? Or on the categorical data set, right? Here we are only selecting the categorical columns and then we are transforming it. Once you transform it, you can check all the categories with the categories attribute, right? And here, after that, we are just trying to here we are just trying to print out the result, and we can see that for each category, right, we have the binary columns, right? So this is how the one hot encoding works, right? So now, yeah, so this is it. This is it with this pre-processing and the pipeline, right? So now we have learned all the pre-processing tasks. So basically, we have learned some common pre-processing steps like imputation, scaling, one-hot encoding, right? And we have discussed about this pipeline, like how do we build the pipeline, right? Now, the problem is the different transformations required on a different columns, right? So on the numeric column, we need to apply the imputation and the scaling. On the categorical column, we need to apply imputation and the one hot encoding, right? Now, the next time we'll talk about the column transform, right? For now, thank you very much.